All right, welcome to module number 21. In module number 20, we provided some motivation for optimization material, and now we're going to look into dynamic programming. So what is dynamic programming? Wikipedia describes that in mathematics, management science, economics, computer science, and bioinformatics, dynamic programming, also known as dynamic optimization, is a method for solving a complex problem by breaking it down into a collection of simpler subproblems, solving each of those subproblems just once and storing their solutions, ideally using a memory-based data structure. So we already talked about how dynamic programming involves a situation where there's a past, a present, and a future, and there's a dynamic nature to the system. Decisions, actions that we're taking at this time impact its future situation, and we could suppose that we have a long horizon into the future, 20 steps into the future. We could, through a brute force search, suppose that we have 5 different possible actions at each of these 20 steps. We could look at 5 to the power of 20 possible trajectories through brute force, calculate each of them computationally problematic. Instead of that, the dynamic programming, it breaks them up into simpler subproblems and solves them recursively one step at a time. And at a high level, what we're going to show over the next several slides is a dramatic reduction in computational needs, okay? So it resembles divide and conquer. We have a large problem. We're going to be partitioning it into parts. And again, the dynamic nature of the problem links the past, the present, and the future of the system. And we want a decision and an action whose combined costs, the current costs plus the future costs, that recall the current action is going to alter the future trajectory, and therefore future costs that we may incur are impacted by our current decision, our current action, okay? So whereas brute force optimization is computationally intractable, dynamic programming is completely reasonable. So here's our problem setting. Lowercase t will be time, capital T will be the time horizon, the maximal amount of time being considered. Later we'll briefly discuss a situation where we have an infinite time horizon, but that's a special case. xt, lowercase t, is going to be the state at time t. So there's a state machine here. And to put that in perspective, so we may have state number 1 and state number 2. Just let's keep it simple, just 2 states. And perhaps we have an input and an action, IN for input, AC for action, input 1 and action 2 that lead us to state 2, and maybe input 2 and action 1 keep us in state S1 and so on. So we have a trajectory, okay? That's the important thing that I'm trying to explain here. And xt is a state at this time in our state machine, and we have a set of possible actions. Omega is a function of xt, and at is the action that we're performing at time t. So now capital T of xa is the next state upon choosing action A. So we were in a certain state in my state machine, and because of the arrow, we're following the action A to the next state. And capital F is going to be a payoff from action A, an immediate payoff. And as I said, there are going to be future payoffs based on the future trajectory that we're taking, and the current action involves an immediate payoff, fx of A, and it also indirectly involves future payoffs. And we want to maximize our payoff up to the horizon, capital T. Minimize payoff, by the way, could be maximizing utility, minimizing cost. So cost, utility, all these things up to a negative sign are the same. We want to maximize our situation, okay? So here's a solution approach. Again, we're heading toward a low computational approach. The brute force approach would be We have capital T time steps. We have some number of possible actions at each step. We're considering every possible trajectory. Our approach is going to be to partition it into steps. Imagine that capital T is the end of the time horizon. And to keep it simple, imagine that the current time, lowercase t, is capital T minus 1. We have one time left for an action. And what that means is that we're going to be paying a cost or receiving a utility right now, fxt of a. And what happens in the future state doesn't matter to us anymore because we're already going to be out of time. So we're going to be maximizing the payoff by maximizing that function f, which is a function of the current state xt with one time step left and the action a. And the optimal a star, will be argmax of the f functions. Now, at time t, we've arrived at state x capital T is the t function of the current state and that optimal action. We don't care about the payoff there. So this is a greedy optimization with one step left. What about if we have 2 steps left? So based on the basis case, right now, we are at time capital T minus 2, and we can calculate the a star for the last decision. So let's try to illustrate this. The horizontal axis will be time, capital lowercase t for time. At time capital T, we do nothing. That's the horizon. So I'm having this dashed line. And at time t negative 1, which we considered in the previous slide, we took the action of x star. And now we're at time t minus 2, and we can optimize the current utility or cost that we're going to receive, f of xt a is right now, plus the next payoff. The next payoff is the utility of the state that we're going to reach at time t minus 1. So we're going to choose the action that accounts for the sum of the payoffs, utilities, costs, whatever you want to call it. The present plus the future. And because we're at time t minus 2 and at time capital T minus 1, we've already calculated that payoff, we've optimized it, we can incorporate that information into this decision. So now we went from capital T minus 1, then we had capital T minus 2. We can simplify things recursively using notation for optimal actions and payoffs at time lowercase t, arbitrary lowercase t. So a star as a function of xt will be the optimal action at time t, given our current state xt. Psi of xt will be the optimal payoff, again, starting from time t, starting from state xt. The basis case provides the a stars and the psis for time t equals capital T minus 1. The recursive case is for t minus 2. A star, the optimal payoff, is the argmax over all the possible actions of the immediate payoff plus the next payoff. And the next payoff is actually the psi function. And just like we do this for capital T minus 2, we can recursively run this for smaller t's. So we proceed as follows. Capital T, there's nothing to do. We're done. 0 payoff. Capital T minus 1, that's the basis case. Capital T minus 2, we solve it through this recursion. Then we solve T minus 3 through this recursion, T minus 4, and so on. And the heart of the matter, the key insight, is that each time we're optimizing the costs for the current payoff plus what we just recursively optimized for a moment ago. So this is the computationally efficient dynamic programming solution. Instead of processing from T up to capital T, the horizon, we reverse the order. first capital T minus 1, then capital T minus 2, then capital T minus 3, where you'll note that the difference between capital T minus 2 and capital T minus 3 is that on the upper line, we're using the psi function, the overall optimized payoff, given that at time capital T minus 1, we're going to have the next state function from our decision at time capital T minus 2. And on the lower line, we're going to make a decision at time capital T minus 3. That decision will lead us to a next state capital T of xt minus 3 and the action A. And that's what the state at time T minus 2 will be. The general case, these are called the Bellman's optimality equations, and it's been proved that they're optimal. In each time step, we're storing the optimal actions and payoffs. We're proceeding from the horizon back in time. We create a lookup table for the size, the payoffs, instead of recomputing everything every single time. And this significantly solves on computation. And this allows us to construct a sequence of optimal actions within the lookup table. So now you may ask, why is this computationally efficient? And let's evaluate this by looking at the computational complexities. The brute force approach, we have cardinality of omega actions at each time step. We have capital T time steps till our horizon. And we have an exponential number of possible trajectories, cardinality of omega to the power of T. And this leads to a computational complexity where if we assume that each of these trajectories can be evaluated at constant time, and maybe not, maybe it requires, let's say, theta of T time, because we need to sum up T payoffs. Then, but at least under the assumption that it's constant time, the computational complexity is theta of cardinality to the power of T. In contrast, for dynamic programming, one step at a time, we're examining all the possible actions, and we're doing that for capital T times, and therefore the cardinality of the number of actions times the time horizon, the overall complexity is theta of that. So whereas the brute force optimization is computationally intractable, exponential growth, dynamic programming is very reasonable. I said earlier that there are different variations. For example, the infinite horizon case. In the infinite horizon case, the decision problems require a discount factor, beta, to give future payoffs at time t a lower weight, beta to the power of t, means that the more that we go into the future, the more that we discount that future payoff. And the reason for that is as follows. If we have an infinite time horizon, well, we can't really solve this for every single time step. But what we do want, we want the same policy at each period of time, but the payoffs in the far future matter less than the payoffs right now, which is why this discounting factor beta will be less than 1. And we're going to calculate something like, you can think of it as a steady state action policy, that given that we're in state xt, we're going to have an optimal action to perform for that state that leads us to state x at time t minus 1. So that's finite versus infinite horizon. Another variation on this dynamic programming theme is deterministic versus random. So far, I described a next state function and a payoff, which is deterministic based on the action, but the next state and payoff could be random. For example, the number of users might be varying, and our action is to adjust the server to account for a possible future trajectory of the software where the number of users is unknown, the possible users that interact with us in the future, and therefore we can optimize maybe the expected case or the worst case or the 73rd percentile case, but it's not deterministic. Yet another variation is a differentiation between discrete time and continuous time. So far, I've discussed discrete time steps, t, t plus 1, t plus 2 up to capital T, and there could be continuous time. We're now going to have a comprehensive example, which is taken from the textbook by Corman et al. This is a rod cutting problem. We have a rod of integer length n, and we have a table of prices, pi, that's charged for rods of length I. So you have this long amount of material, let's say 100 feet, and you can cut it into rods of length 1 foot, 2 feet, 3 feet, 4 feet. And now we're asking, how do we cut it in a way that our overall revenue, this could be revenue, could be profit, but our utility will be optimized. And to keep it simple, suppose the cutting is free. If it's not free, we would make a minor variation on what we're optimizing. And we want to cut rods into parts, or maybe not cut it at all, to maximize our profit. So we're going to have a rod of length 4, and we can charge prices of, if we have a 1 foot rod, we get 1 unit of money. Let's call this dollars, okay? If we have a 2 foot rod, we get $5. For 3 feet, we get 8, and for 4 feet, we get $9. So what are the possible cuts that we could do? Well, A here means we do nothing. We don't cut. We have a single rod of length 4, and we get $9 for that. B means that we cut it into 2 parts. One of them is 1 foot each, or well, not each. One of the parts is 1 foot long, and the other is 3 feet long. For the 1 foot, we get $1. For the 3 feet, we get $8. The total is $9. This $9 is identical in part B to what we had in part A. Now, in part D, skipping over C temporarily, instead of 1 unit then 3 units, 1 foot then a 3 foot rod, we have 3 followed by 1. So we flip the order. And at least for this dynamic programming problem, flipping the order doesn't change how much money we can sell it at. $8 for the longer one, $1 for the shorter one. And yeah, well, it's the same $9 total utility as before. There are dynamic programming problems where the order does matter. That's why this is what may seem trivial, may actually in some other modified problems be interesting. For example, this discount factor that I told you about, getting $8 right now and $1 tomorrow is better than getting $1 today and $8 tomorrow. Now, today, tomorrow, maybe the diminishing value of money is exceedingly slow, so it doesn't matter. But you can think about this as, do I want, let's say, I want to sell something for $100,000 this year, and then I'll have $500,000 next year, or vice versa, maybe $500K now and $100K next year. And probably when we're talking about no longer $1 plus $8, but $100K plus $500K, number one, this is starting to be more appealing. And number two, when you're talking about this year versus next year, having a few hundred extra K in your account for a year is probably beneficial. Now we skipped over solution C, cut it into 2 parts of length 5 each. I'm sorry, length 2 each. Each of those length 2 rods is worth $5. The total of 5 plus 5 is $10. Solution C is better than A, B, and D. Now there are other solutions. We can make in part E a 1-1-5 sort of cut, or a 1-5-1 or a 5-1-1 in parts F and G. As we described a moment ago, this is symmetric, so E, F, and G are all the same utility. $5 plus $1 plus $1 is 7. So these are, for now, the worst solution that we've had so far, because earlier we immediately got a $9 solution in parts A, B, and D. Our last possible solution is solution H. So we went from, in part A, a single rod, in B, C, and D, 2 rods, where the mid solution, C, of 2 equal valued rods, $10, was the best so far. E, F, and G were 3 rods, so we need to cut twice. And H means 3 cuts, 4 rods, each of them of length 1 unit, $1 times 4 is $4. So H is the worst of all these combinations, C is the best. But again, that was a brute force solution. When we're talking about a problem of size 4 and partitioning a rod, and that's doable. we could manage to write these solutions by hand. And if I went from a length 4 rod to a length 6 or 7 rod, this would still be maybe a bit more tedious, but you could solve it on 1 or 2 pages. But what if we have 50? So that's going to be pretty complicated. So now let's use dynamic programming. It's simply unrealistic to consider cutting configurations for large n. So the basis case will be we have a rod of length 1, and there's no action to do. We can't cut it into sub length 1 parts. So our payout, psi of n equals 1, is the payout for a rod of length 1, which is 1 unit. We called it $1. And now let's start running recursions. N equals 2. The payoff for a rod of length 2 is the maximum of 2 possibilities. Either 2 times the payoff for a rod of length 1. Now, some of you may be paying attention saying, hey, for a rod of length 1, we're getting P1, we're done. Well, I'm trying to frame things in terms of the recursion. What we just said, your intuition there is correct. But the point is, we want to think in terms of the recursion, that we're using 2 times what we calculated earlier, the psi of 1 function, or we don't cut and we get P2. 2 times psi of 1 is $2, P2 is $5, and we want as much money as possible. P2 is better. So if we have a length 2 problem, n equals 2, the optimal action is not to cut it, maintain a rod of length 2, sell it at $5. And the utility is psi of 2 is $5. What about n equals 3? So what are the possible actions here? I could have no cuts at all, so that's P3, or I could cut it into 2 parts of length 1 and 2. Now, you can tell me that I can also cut it into 3 parts. So I could do a 1, a 1, and a 1, but actually the moment that I cut 1 part away and I'm left with psi of 2, we've already calculated psi of 2. So realistically speaking, we have either psi of 1 plus psi of 2 if we cut 1 off, or we have psi of 2 if we cut 2 off, or P2 if we cut 2 off and we sell it, plus psi of 1. Now, P3 is $8. Psi of 1 plus psi of 2 is $6. So overall, $8 is better. And for n equals 3, the optimal action is to do nothing, to sell it, no cutting. At each stage, we're maximizing over psi of k plus psi of n minus k for a cut of k, and then the rest we're dealing with recursively. And for k equals n, we're using, well, we could use Pn, or another possibility would be to just look up our function. So psi of 7 is either, well, it's the maximum of all the following, either psi of 1 plus psi of 6, or psi of 2 plus psi of 5, or psi of 3 plus psi of 4, and so on. Or if there's a payout function for no cuts at all, P7, that's also possible. Finally, I want to conclude this module number 21 on dynamic programming by discussing an application of dynamic programming. So in module number 20, I discussed a truck driving application where you're deciding whether to accelerate ahead of a hill, and then while going uphill, slightly allow the gravity to reduce your speed, and then while going downhill, allow the gravity to increase your speed. Or you could just basically run cruise control, do the whole thing at 70 miles an hour, which would mean running a lot of gas and basically exerting your engine on the way up, whereas on the way down, we may actually need to be hitting the brakes. So here's another application. A very well-known application that all of us on our phones are using this application, the Viterbi algorithm, named after Andy Viterbi, the gentleman whose picture we see on the right. And just as a personal note, I've actually had the pleasure, I've run into Viterbi on a few occasions. So what Viterbi showed is that dynamic programming can be used to perform decoding in a communication system application. They're convolutional codes, and in CDMA, which is a communication protocol, Viterbi showed how to use dynamic programming to optimally decode the convolutional codes. A similar approach, it's called the Viterbi algorithm, is also used in speech recognition. And in speech recognition, the text is hidden, and we have speech observations which are a waveform, but they're noisy, and they help us estimating the text. The Viterbi algorithm relies on a trellis diagram of the trajectories of how we're evolving between states, and it relies on dynamic programming and tries to find the shortest path. Not shortest in terms of the number of states that we're crossing, we always have the same number of states, but the lowest cost function, shortest in terms of lowest cost within this diagram. So that'll be it for module number 21, and we'll continue next time.